Okay, so this time around we have this example, and again we just want to draw the shear and the bending moment diagram for the figure shown. So this is a little bit tricky because now we have a distributed load, but still it's the same concepts we're going to use here. And the first step is a free body diagram of our structure. So we have supports at this point and at that point. So let's understand what these supports are. What are they giving at the respective points? So for this structure, we can label this as point A here and point B here. And let's label our structure. So let's draw it. Okay, so we have point A and point B. Then right below it, we're going to have the two diagrams. So shear force will come here. U by 9 is 27, right? Yes, it is. Yes, it is. So first thing, draw a free body diagram of the structure. Yeah, mind what is happening at the ends. Once you have the free body diagram, since what you have is a distribution like this, you know to say from CEE, the position of the effective contribution will have to be a third from this end. So in this case, a third, 1/3 of 9 is just going to be 3 meters. So we know to say this 27 kilonewtons is going to be exerted at the, it's going to be felt as if it was concentrated 3 meters from that end. This allows us to easily get what the reactions are. When you sum forces in the x-axis, for example, and equate to 0, you see that we only have AX. So AX here has to be equals to 0. Because AX is 0, we might as well leave it out from our analysis. So we can just remove it and remain with this. When we sum forces in the vertical axis, we see that you have AY going up, BY going up, and then that 27 going downwards equals to 0. So we have AY plus BY equals to 27. Let's hold on to this one. Now to find one of these, we're now going to take moments. So let's take moments about point B. And equate to 0. We see that if we take moments about B, the 27 will be causing an anti-clockwise rotation. So it will be 27 by 3. AY will be causing a clockwise rotation. So it will be minus AY. And the distance it will be the full length from A to B, which is 9, is equals to 0. So now we have AY is equals to 27 by 3 over 9. This will go 3 times there so that we have 3 by 3, which is 9 kilonewtons. And having found AY, we can easily get B1. This will be plus 9 is equals to 27. AY will be equals to 27 minus 9, which is 18 kilonewtons. So which one did I go for? Oh, okay. So I think here I put 9 at BY. This should be at AY since AY is the one we got as 9. So this is 9 here plus BY. So at BY is the one that comes out as 18 kilonewtons. Now that we have the support, what is happening at the supports, let's include them. at A, we saw to say that we had 9 kilonewton force here. At B, we saw to say we had 18 kilonewton. Okay, now everywhere else between we have that distributed load. So everywhere else between we have the distributed load. Let's show the distributed load. So this is stretching from here, going all the way up to the far end. Okay, so this is what we have here. Maximum 6 kilonewton per meter. Okay, so with this done, now we want to understand what is happening to this structure. We see that we don't have a concentrated force at any point. What we have is a distributed load. That is quite tricky. So to understand what is happening due to that distribution, we are going to start picking our sections. All we have is point A to point B, and everything else between is controlled by that distribution. So let's pick our section. So when we pick our section, we can cut it at any point really. Again, we see that the behavior here can be extended as long as there's no sudden change, because everywhere here it's going to be concentrated by that distributed load. So we can discuss what happens for a small section, and then try to see if we can extend that idea to the whole structure. So let's split it up to that point. Let's draw the structure just up to that point, and let's see what we have. First, we have this section of our structure. At point A, we have that 9 kilonewton. I'll pick the section to the left. Then, right at the point where we have sectioned it, we're going to have the shear force. And we're also going to have the bending moment. But this is a distributed load. It's still going to be present here. And this was in its early stages, if I would call it that. But you have to see that in this case, it will not necessarily be going all the way up to the 6 kilonewtons, which is at its peakmost end there. So this will be slightly less than that. Okay, so how do we describe what is happening here? So now the tricky part is understanding how the distributed load is affected. We know to say we have reduced, you see, this was the whole structure. And for the whole structure, the length from A to B, the length was 9 meters. And when the length is 9, the maximum force at its peakmost point there, we see we have a 6. Now, what if we scale it down? What if we reduce the length of the beam to a value x? The question is, how much will the distribution at its peakmost point reduce? Let's label this as W. So how much would that actually be affected? So we want to get what this is going to be if the length is reduced to half. You see, by proportion, these are actually related. So let's start with the sides. So when it is in its original shape, we see to say that we have a load of 6, a maximum load of 6, corresponding to a full length of 9 meters. This has to be equivalent to how the length will also change. The lengths here, so the 6 and the 9, this is the load, and this is the length of the structure. So here, the load now, when it is reduced, the load, what would the new load be? if the length is reduced to a variable x. Because we're keeping a variable x because we don't really know exactly where this is going to be reduced. So we're keeping it general. From here, we see that actually the load is not going to have a fixed value. But what the expression for the load will be, it will depend on what x is. This will be the expression that tells us the load distribution. It's going to be 6 over 9x. And when we simplify this, we get 1 over 3x. What this is telling us is, if you are further away from this, because our x will be measured from point A here, the further your section is, the greater the distribution will be, which actually makes sense because by the time you go 9 meters from B, let's try. Here we have W is equals to 1 over 3x. By the time you go 9 meters from B, meaning x is now 9, you're going to have 1 over 3 times 9. And 1 over 3 times 9, 3 into 9, this is going to go 3 times.
Plus 3?
No. This is, yeah, this actually makes sense. Look at this. We actually made a mistake on this one. Look at this one here. This is 6 over 9. 6 over 9 doesn't reduce to 1 over 3. 3 here will go twice, meaning we're going to have a 2 on top. I did go to actually check it out because otherwise we would have been using a wrong value. Yeah. So this is 2 over 3. So we see that our expression here is 2 over 3. So let's check it now. At its full length, when the length, if we pick our value of x as the full length, which is 9, we now have 2 over 3 times 9. Let's see, 3 into 9 goes 3 times. 3 times 2, which is 6. Guess what? It actually does give us the load distribution for the full length, which is what we wanted to see. So this expression for the distributed load 2 over 3x, it now gives us to say, okay, you don't have to be specific about x. As long as you know what x is, you can get exactly what the distribution will be. So for our analysis where we have selected our section here as just to say it has a random length x, this becomes perfect because now we have a way of also checking what our distribution will be. So our distribution here will be given by 2 over 3x. This is how our distribution will be represented. While the length of our structure, the length, let's say the length from here up to here, it's x. So once we've done that, of course, here the force here is 9 kilo, here we have V, then this is our bending moment, M. Now with this in mind, we can now try to guess where the distribution will be concentrated also. Where would the distribution be concentrated? So to find the concentrated distribution here, since we now have the expression for the distribution, we know to say again, this is triangular. So because the distribution here is triangular, we know to say, to find its effective contribution, we're going to use half because it is triangular. If it were rectangular, something like this, would have just multiplied the full distribution by the length. But because this is triangular, we know we're going to use the area of the triangle, which is half. The length here is just x. So times x multiplying the height, which is going to be 2 over 3x. When we simplify this, we see that we have 2 and 2 cancel, so that we have 1 over 3. X and x gives us x squared. So this is what we get as the expression for the combined or the overall distribution. So in other words, we can look at the distributed load as if it was just one force. Again, before I remove it, it will just be one force acting at one point. But what point will that be? We know it will definitely not be the center because this is triangular. It is more concentrated near this end than this end. So it will be closer to this end. But how close? Again, this is where we use centroids to say that it will be a third from this end, a third of the full length. So since the full length is x, a third of x will be 1 over 3 of x. So it will be, we can approximate it to say that this is going to be concentrated here. So remove this since we're going to represent it by that red line. So, and we don't need this anymore now. All we know is that the distributed load, it will be represented by 1 over 3 x squared. It will be concentrated at this point, and this point is some distance from this point, from this edge. And what will be this distance? This distance is also 1 over 3 of x. So I hope you know, don't confuse this 1 over 3 and this 1 over 3. This one is determined in CAE to say that if you have a triangle of this nature, its center of mass will always be, if this is from here to here, if this is B, then the distance from here to here will be 1 over 3 of the full base. This is where the center of mass will be from centroid. Okay, so having done that, we can now start finding the shear force. To get the shear force, just sum forces. Sum of forces in the y is equals to 0. We see that the 9 goes up, positive. The shear force, the V here goes down, negative. And the concentrated load also goes down. So you have minus 1 over 3 x to the power 2 or x squared. They are the only two, so this is equals to 0. We make the shear force subject, it goes to the right. We now have V is equals to 9 remains, 1 over 3 remains, x squared. This is now our expression for the shear force. But what does this represent? This represents a quadratic equation. And a quadratic equation can either open upwards or it can open downward. But to know which one you're dealing with, look at the coefficient of the x squared term. The x squared term is here, and its coefficient has a negative there. Because it has a negative, we know it has a maximum turning point. So we're looking at this type of quadratic based on that negative there. And with that in mind, we know it's curving downwards. All we want to now know is at its starting point, where is it starting from? And at its end point, where is it ending at? So when you look at our graph here, we don't see any drastic change between to affect the force. You only have that distribution. So at this point, what is the value of x? Here, x is equals to 0. At the furthest point, before we see any change, it's at point B. At point B, x is equals to 9. So I want to now know what is going to be the shear force at x is equals to 0. If x is equals to 0, we see that the shear force is 9 minus 1 over 3 times 0. We see that the shear force is 9. So this is where we're starting from, at 9, positive. Remember, the unit is kilonewton because of that distributed load they gave us. So in other words, for our shear force diagram, we are starting from positive 9. So you can place it here at 10. We're starting from here. But how about at B? Where are we going to be? At B, the length there is a 9. So you come to this equation again. Now we say, okay, what about when x is 9? What will be the shear force? When x is 9, we have 9 squared there. So you have 9 minus 1 over 3, multiplying 9 and 9. This will go 3 times. We now have 9 minus 3 times 9. Here, I can even say 9 out here since I want it to be less. But anyway, this is straightforward now because when you combine these, you're going to have this will be 27. And then 27 from 9, we get negative 18. So we see that at the far end at point B, the shear force will be negative 18 kilonewtons. So when it comes back to our diagram, we see that at point B, we are in the negatives. So at point B, we're in the negatives somewhere here, and even Let me just shift this one downwards. So at point B, we are at -18. So in drawing our structure, there's a high chance it's like this. There's a high chance that maybe it is like this. Or this is possible. But all we know is it's curving downwards. So it can be one of these. So I'll leave it as a curve for now. Keep it like this. I can to understand where exactly whether it's still going up before going down. I would have to first know where the turning point is. For now, the only thing I'm more interested in is this point here. We can find, of course, where the turning point is, but more importantly, this point here. What is it? What is the value at that point? You can literally try to find the value of x at that point. We know this expression is governed by 9 minus x squared over 3. So I want to find exactly the value of x at this point. So I'll just use this expression. Because at this point, I see that the shear force is what? The shear force is 0 there. So just come back here. The shear force expression was 9 minus x squared over 3. So what will be the value of x when the shear force is 0? So I see that now I have 9 minus x squared over 3 is equals to 0. X squared over 3 is equals to 9. And then I have x squared is equals to 27. And finally, x is equals to root of 27. The root of 27 will come out as 5.2 meters. So that is the value of x at that point. We'll keep it. It will be important later on. At this point, x is 5.2 meters. Generally, this is the shear force diagram. So we have it has this part here, and it also has this part here. So with the shear force sorted out, now let's look at the bending moment diagram. For the bending moment, we're just going to use what we already came up with, which is this, which has the distances in place. So what are we doing here? So for this one, we're going to take moments about where the section is. So we're going to take moments about this point. So there, of course, we have our moment M anti-clockwise. So we studied that one. And then we have the distributed load also causing an anti-clockwise rotation. The load itself is 1 over 3 x squared. But the distance from where it is applied, notice that that distance is 1 over 3x. That is what that distance is. Then what else? You have the 9 kilo causing a clockwise rotation, so minus 9. The distance, here it is just x, is equals to 0. So now you just have to simplify this. 3 and 3 will give us 1 over 9. So now it'll be x to the power 3 minus, here we're going to have 9x is equals to 0. So that now we have m is equals to 9x becomes positive, then minus 1 over 9 x to the power 3 as the expression for the bending moment. Now what do we see? Our expression here is a polynomial of degree 3. And what do we know about such polynomials? They turn twice. They have 2 turning points. But here, our key interest is what is its value at point A, and what is its value at point B. At point A, x is equals to 0. So at point A, x is equals to 0. Because of that, when we plug in 0 where there's x, notice that the bending moment there will be 0. So for the bending moment diagram, we see that it's starting from here. Next, how about at point B? At point B, x is 9. So there, we're going to have put 9 where there's x. So this is what we have. And in this case, we're going to have 9 by 9 minus, this will be 1 over 9 multiplying 9 to the power 3. We said this will just cancel with 1 from there. So at either end, you have 81 minus 81. And this will be equals to 0. So that will be equals to 0. So what we see is that in the end, our bending moment diagram starts from 0, and at point B, it will also be at 0. But where are we going? Are we going up? Are we going down? To understand that, we just want to understand exactly what will be our moment at that point. Turns out that that is where our maximum is going to be. When it comes out to that, we found the distance there to be what was that, 5.2? See, the value of x at that point, did we label? Yes, we did. The value of x there was 5.2. So what will be the bending moment when x is 5.2? So we come to the expression for the bending moment and put 5.2 where there is x. We see that this is going to be 9, 5.2 here, minus 1 over 9, then 5.2 to the power 3. If you work out this, you get 31.2 as the bending moment. So meaning at that point, at this point, the bending moment is going to be at 31.2. So we can now complete our curve. So this is going to be something like this, passing through that point, and then coming back down to 0. So basically, this is what we're going to have as our bending moment diagram. And of course, here we know to say at this point, this has to be at 31 point, just at this point where it passes 5.2 here meters. That is at 31.2.